Alright, welcome back everybody. In this video we're going to talk about particulate motion in algebraic, from an algebraic standpoint. And the entire first page of this lesson defines various characteristics of particle motion in terms of slope ideas and derivatives and things that we've talked about already in this course. It would be a good idea for you to read through all of these from the note sheet and make sure you understand what they are. A quick rundown of them. Average velocity is just displacement divided by travel time. So that's a slope calculation. It's finding the change in position over the change in time. Instantaneous velocity is the derivative of the position function. So if we have a position function, we can find the function that represents the instantaneous velocity by taking the derivative of the position function. We have speed. Speed is the absolute value of velocity. So in order to find the average speed, we can take the absolute value of the average velocity. And in order to find the instantaneous speed, we can take the absolute value of the instantaneous velocity. So just the absolute value of the derivative of the position function. Another characteristic that we run into in particulate motion is acceleration. Acceleration is the derivative of velocity, and therefore it is the second derivative of the position function. We'll use that one every now and then. And we have some higher derivatives that are a little bit more obscure. We talk about the jerk here. The jerk is the derivative of the acceleration. So it's the second derivative of velocity and the third derivative of position. There are even higher order derivatives that we use to talk about some really obscure characteristics of particle motion, but we're not going to talk about them here. We'll stop with jerk. And I only stop with jerk just because it's fun to, be able to talk to someone you know and just be like, man, you are the third derivative of a position function. Unless they've had, some calculus, they have no idea what you're talking about, and you can feel some satisfaction at calling them a jerk without them knowing. All right, on to the examples here. Example 1. While pacing back and forth in front of my classroom one day, my position can be described by the equation x of t equals, and you see the equation there. Using this information, answer the following questions. All right, first, what is the average velocity over the first 3 seconds? So we're talking about average velocity here. So this is going to be a slope calculation. I want my position at time 3, since that's the end of the time interval, minus my position at time 0, all over the change in time. And I calculate all those things. Let's see, x of 3 is going to be 27 minus 54, that's negative 27, plus 15, that's negative 12, plus 3, that should be negative 9. And my position at time 0 should be 3. All over that time interval. So I get negative 12 over 3. And my average velocity, it doesn't tell me what my units are, does it here? Let's call it feet. We're going to say this is negative 4 feet per second. Okay? My instantaneous velocity after 4 seconds. In order to find instantaneous velocity, I want to get the velocity function. Velocity is the derivative of position. And so I'm just going to go ahead and take my derivative for this position function with respect to t. It's going to be 3t squared minus 12t plus 5. And so my velocity at time 4 is going to be 3 times 4 squared minus 12 times 4 plus 5. And if I calculate that, I end up getting that this velocity is 5 feet per second. All right, the next question. What is my acceleration after 3 seconds? So in order to get that, I need my acceleration function. Acceleration is the derivative of velocity. And so I'm going to take the derivative of my velocity function that I found in part B, and I get my acceleration function. It's going to be 6t minus 12. And then to find my acceleration after 3 seconds, I'm going to substitute 3 in here. And I get that my acceleration at time 3 is going to be 6 feet per second, or 6 feet per second squared, as my acceleration after 3 seconds. Alright. Question D is an interesting one. When did I change directions? When did I change directions? And if you think about what's happening when we move, from left to right as I pace in front of my classroom, I'm moving to the left, and then for an instant I stop, and I move back to the right. Okay? And where I move to the right, and then for an instant I stop and move back to the left. Well, what happens when I change directions is that my velocity either changes from being negative to being positive, or from being positive to being negative. So we're looking for where the velocity changes sign. And that's going to happen in this polynomial function. That's going to happen when the velocity is 0. So we're looking for where v of t is equal to 0. That'll tell us the time where we change directions. And so I can take that function, 3t squared, the velocity function that we found in part B, and set that equal to 0. And I can solve for t. Oops, that's a 5. Not 15. My reading skills are not top-notch today. So we want to find out when this function is equal to 0. And we can do that either by factoring, if we can factor this, or using the quadratic formula, or using our graphing calculator to help us. I'm going to go ahead and use my graphing calculator. I'm going to go to my y equals, and I'm going to graph 3x squared minus 12x plus 5. And I'm going to solve this equation by looking at the graph. And hopefully we'll see, okay, we see a couple places where when I change direction based off of this velocity function. So I'm going to find both of these. And one of the things you can do on your AP exam without showing any work is solve an equation. And this is a really good way to do that. Just go ahead and take that function, graph it, and find out when it's equal to 0. So I'll use the 0 command and find the first intersection point. I'll guess 0.472 seconds. And I'm actually going to keep some more digits here in anticipation of question part E, 47477. So that's one of the times when I change directions. And the other time when I change directions is the other intersection point, or the other root of this function. And so I'm going to go ahead and find that one. We get 3.527. 527. 5252. Okay, so those are the times when I change directions. Now, in part E, it asks me where was I when I changed directions, and in order to find that, we need to go back to our original position function, t cubed minus 6t squared, plus 5t plus 3. Alright, that's my initial position function. And in order to figure out where I was, I'm just going to go ahead and substitute those times into this position function. And figure out what my position was at those times. The easiest way, I think, to do this is just to go ahead and now put my position function in here into my graph screen. And since both of these times are going to fit into a standard window, I want you graph. There you go. I'm going to have it make a graph there of my position. And if I trace this, I can type in the first x value, 0.47247477. And my y coordinate will give me my position. I'm going to round that to 3 decimal places. 4.128 means I was 4.128 feet from the origin at that time. We'll do the same thing. I'll trace it again, and I'll type in my other time, 3.5275252, and I get negative 10.128, and that's my position in feet the other time I change direction. So I'm 10.128 feet to the left of my origin. Alright, and question F, what was my position after walking for 2 seconds? So all that is my position at time 2. So I put 2 into the position function and calculate. That's 8 minus 24, negative 16, plus 10, negative 6, plus 3, negative 3 feet. So I'm 3 feet to the left of the origin at time 2. And then lastly, what was my displacement after 4 seconds, which is a little different from my position. My displacement is my change in position. So after 4 seconds, my displacement is going to be the difference between my position at time 4 and my position at time 0. I can calculate both of those by putting those values into the position equation. So I put 4 in. That's 4 to the third is 64 minus 96. That's negative 32. Plus 20 is negative 12. Plus 3 is negative 9. And at time 0, my position was 3. And so my displacement is negative 12 feet. What does that tell me? That tells me that over those 4 seconds, I moved 12 feet to the left from where I initially was. Alright, that ends this video on an algebraic perspective on particulate motion. See you next time.